and certain partial differential equations called Hamilton-Jacobi equations. So just to clarify the beginning of the title, I use mean field disorder systems as a not so short keyword to replace spin glasses and the class of problems of statistical inference that Lenka talked about this morning. So I'm going to report on works that have been written by various subsets made of Hongbin Chen, Thomas Dominguez, Naming Shah, and me. All of us are here in this conference. And the goal is to study these mean field disorder systems, and in fact, to be more precise, is to compute the limit free energy that is associated with these things, or maybe in the context of statistical inference, compute the mutual information between the signal we care about and the observation that we are given. This is the only question I think about, basically, for the purpose of this course. And we try to think about this question using ideas from a partial differential equation. The fact that there might be some partial differential equation behind the arguments that we are used to is not new. It's already present in the original paper of Francesco Guerra, who introduced the interpolation method with the replica symmetry broken bounds. But we try to maybe take this to heart and to develop it to the best of our abilities. And this is what I'm going to explain now. So to start with, I would like to discuss a very simple model. And I apologize already to speak about such a simple model in front of such a distinguished audience, but I promise you that this is a good way to understand, first of all, what we try to do, but also to really display in a very precise way what are the technical difficulties that show up when we also discuss the more difficult problems. And the problem I want to discuss is to study the Curie-Weiss model. So there are lots of ways to understand this thing, and by understand I mean compute the limit free energy. Let me write what this free energy is. So 1/n log of the partition function. So it's also a model on Ising spins. Plus or minus 1. It's a mean field model. There is no geometry. If you want to think about it like this, it's like a spin glass model, except that the couplings are taken to be equal to 1. So the whole I and j between 1 and n. And then I'm going to also have a magnetic field. So T and H are parameters that you fix in advance. Let's say T is non-negative and H is a real parameter. And for each T and H, you want to understand the limits as n goes to infinity of this quantity. So, and let's say we want to do some partial differential equation arguments. So let me compute derivatives of this object, which also will clarify why this object is interesting, I guess. So if I differentiate with respect to this H parameter, so I have a log here, so the derivative will be the ratio of the derivative of this sum divided by the sum itself. The derivative of the sum will look like taking this sum over sigma I and writing it in front of the exponential. And so, in other words, you will be computing the Gibbs average of sum of sigma I for the Gibbs measure associated with this energy function. Okay, and there's a 1/n in front. So if I denote by this bracket the Gibbs average, this is the derivative. Does everybody see if I write here? Yes. And similarly, if I compute the time derivative, then, well, something similar will happen, except now this is the quantity that we pop out. And the fact, the fact that this model is very simple is related to the observation that this quantity is actually a function of the magnetization itself. And so you can solve this by not comment on it. So there's something interesting that will relate this t derivative, I'm going to call it the time derivative, okay, with this derivative squared, because you see that the difference between this and this squared is the variance of the magnetization. And plausibly, this is small, okay, at least for most choices of the parameters. And moreover, you know, at least one way to think about this quantity is as some sort of a Laplace transform of the variables you care about. And here, you know, when we compute this minus this squared, this is about the second moment of the magnetization. It will be related to the second derivative in h of this quantity. And I'm not going to leave you in suspense. If I do the calculation, I get this. So this variance is n times the second derivative in h of f. Okay, it's a simple calculation which I don't plan to do here. Perhaps one last word of comment, so we already have an evolution which is completely closed. Now we can almost forget the original question and just study this equation. And I said almost forget because I have to also specify something about the initial condition. I'm going to call it now. You know what happens with Fn when we set t equals 0. But this also is very simple. So the quantity is still displayed here. If I set t equals 0, I just have the sum over sigma I. This is a sum with no interactions. So it completely factorizes. If you want to think that way, it's like exponential of the sum. So you can write it as a product of exponentials. And then with the sum, everything factorizes. And in fact, when you set t equals 0, this quantity does not depend on n. Okay, so you can completely specify what I'm going to call the initial condition now, and it simply does not depend on n. Okay, so now we can completely forget about the spin model and just take these two pieces of information as input and ask what is the limit as n goes to infinity of a function that satisfies these two properties. I think it's quite intuitive to just decide, sorry, I wrote n, but I meant 1 over n. Sorry about this, which sounds much nicer. Are there questions so far, or did I make other mistakes besides this one? Time to go to sleep? Not yet, not yet. So there's a 1 over n, so I think it's quite intuitive to believe that as n goes to infinity, this is going to disappear. And so in the end, we're going to say the limit of Fn is the solution to the equation where we set the right-hand side to be 0 with this initial condition. Okay, so let me state this. Let's say this is a proposition.
Provided the second derivative has a nice behavior in it.
Right. Yeah. But at least as a heuristic guess to start with, it feels plausible that maybe this is going to happen. I'm going to state it as a proposition because I'm very confident. Okay, and in order to make rigorous sense of this statement, in fact, I think the most difficult aspect is to just make sense of what it means to be a solution to this thing. Once we agree on what the solution to this thing is, then okay, the proof comes because we have clarified that. And the reason it's not entirely obvious is that you could say, but the solution to this is a C1 function that satisfies the equation. What is the problem? But if you know about the Curie-Weiss model, or if you've heard Lenka talk about phase transitions this morning, or if you know about the Ising model, you expect that this quantity will not vary smoothly as a function of the parameters. You expect that when t is sufficiently large, you expect the sigmas to be coherent, And so when t is sufficiently large and h is just a little bit positive, this will be positive and bounded away from 0. And then if you move to the h close to 0 but negative, this will be away from 0 and negative. Okay, so it will have a jump. So you expect the derivative to have a jump. So you don't expect the function to be C1. So you cannot just say, oh, function is C1 and solve the equation. What is clear though is that the function will be Lipschitz, because we see, it's obvious in these expressions that these derivatives are bounded by 1 in absolute value. And you may or may not know, but any Lipschitz function is differentiable almost everywhere. So you can say, okay, fine, it's not C1, but differentiable almost everywhere. So I'm just going to say a solution to this thing is a Lipschitz function which almost everywhere is differentiable and satisfied. Okay. Now you have the opposite problem to the previous one. The previous one was that if you say f is C1, there is no solution to the problem. Now the opposite problem is that if you just prescribe what I said, then there's an infinite number of solutions to this problem. So perhaps I don't have time to explain this, but it's very easy to cook up examples of many examples of solutions of this problem if you just prescribe what I said. The reason is that if you have two things that solve the equation almost everywhere, you can glue them together, and the point where the gluing occurs is of measure 0, and so this will still be a solution. So for instance, if you start from the 0 initial condition, you can create a corner that then starts to grow, and this will be a solution, and you can make your corner appear anywhere you want, at any time you want, many corners if you want. That is still not good enough. And PD people have thought about this quite a bit, and they have converged on the notion of solution to this problem, which is the notion of viscosity solution. And I don't have time to give you the definition of this, but historically the way it was defined was actually just precisely to say, well, we're going to say the viscosity solution is that thing which we obtain by solving something with a small viscosity term like this, and then letting the viscosity go to 0. So I don't want to give you the definition of viscosity solution, but one aspect I want to emphasize is that before we pass to the limit n goes to infinity, this equation satisfies a property which we can call the maximum principle. If you want to think about it like this, you can think of this as a monotonicity property. And that monotonicity property is that if you start from two initial conditions which are ordered, one being above the other, then this ordering will be preserved by the evolution. Okay? And you want this monotonicity property to still be valid for your notion of solution in the limit. Okay? And essentially, like any scheme, like any way you approximate this solution that respects this monotonicity property will be a valid way to approximate viscosity solutions. Okay, so if you want, as a heuristic way to think about viscosity solutions, it's, it solves the equation almost everywhere, and moreover, it has this monotonicity property built in. All right. Now, why did I really want to tell you about this problem? I wanted to tell you about this problem because I want to emphasize the sort of difficulties that show up when we deal with the real problems that we talk about, the more difficult ones that I mentioned earlier. And do I have corner? Is that for this simple model, it's a bit of a miracle that we have an exact identity for finite n. This will never occur in practice when we deal with more complicated models. And usually what we get is something like this, with absolute values and then bounded by. Okay. But from the point of view of this theory of viscosity solutions, this is horrible. Because viscosity solutions are made in such a way that you remember that before we passed through the limit, you had the plus Laplacian in your equation. Okay? If you have minus Laplacian, then you're solving the backward state equation, and if you think about it for a second, you will see that this is not going to satisfy the monotonicity property I was describing. But if I have absolute values like this, I don't know if I'm solving the forward equation or the backward equation. And so what do I do? What is really nice with the toy model is that you can see that this is not an artifact of your limited technical abilities. It really occurs that sometimes you deal with a legitimate problem of statistical mechanics that indeed does solve the thing with the sign being invalid. And the way you can hook up examples is by taking just exactly the same model, but you put a minus sign here. Okay, if you put a minus sign here, then this will not change. This will have a minus sign. So it will be a minus here. So what you really want to do is to compensate this with a plus. And what you will get on the right-hand side with no absolute value is minus 1 over n blah, blah, blah. So it really occurs, and we have to find a strategy to circumvent this problem. And one way we found, which we like, I'm going to state now. So this is in this appeared in a paper with Hongbin Chen and Jiamin Xia, and with good help from Stefano Bianchini also. We had discussions with him that were very helpful. It says the following. It says that, in fact, another way to identify that you're dealing with the viscosity solution is to use the fact that the functions we are dealing with are convex. So f sub n is convex in H. That's clear because when we differentiate in H is the variance of this object. And it's not difficult to see that it's actually jointly convex in C and H. So let me state something. So let's say, maybe I'll say it in some general form. So let's H. So maybe you don't know what is the viscosity solution, but you can take this as a definition or a way to select a unique solution to your problem. The statement is that if you take a function which solves the equation you care about, so here I wrote it with some general nonlinearity. Let's assume that, okay, so it's Lipschitz, so it's differentiable almost everywhere. And let's assume it solves the equation you care about almost everywhere. Okay, it has some initial condition, and I'm asking that it's C1. And finally, I'm asking that the function itself is convex, okay, jointly in its variables. If these three properties are satisfied, then I claim f cannot be anything other than the unique viscosity solution to the equation. Okay.
Do we know it exists and everything?
Yes, and also, yeah, it's also true that this equation with this initial condition always has a viscosity solution, and it's also true that if this is convex, then the solution will be convex, jointly in the variables. Yes, thanks for the question. Are there other questions? Yes.
By convex, you mean in both variables?
Yeah, jointly in the variables, yeah, in both variables. I don't know how to make the proof otherwise. But it's true that if the initial condition is convex, the solution will be jointly convex in the variables.
And you only need capital H to be Lipschitz. You don't need anything.
Yes, and indeed, if you feel this result is surprising, I think it's good because, as I tried to demonstrate earlier, the notion of viscosity solution is oriented in time. Okay, it's not the same if you go forward or if you go backward in time. And when you look at this statement and you're not super careful, you don't see any orientation in the statement. So the only place where there is a bit of orientation is when you say the initial condition is C1. Okay, and so it says that if you're a convex function, you cannot create spontaneously a singularity which is not of the right type.
Sorry, there is something that I'm missing. The assumption are on the initial datum that must be C1 and convex.
No, the function is convex. The whole function.
A priori assumption on the
Convexity of your candidate. Yes.
Okay. Instead, if I just assume that C is convex,
Then I can construct counterexamples. For instance, if I start with the flat initial condition, I can create for you a solution that are not zero.
That C is strictly convex.
No, yes, I can construct. So you have to know in advance that that your candidate is convex. Otherwise, so in some sense, at least the one way to interpret this result. So I'm going to give an intuition which actually, if you think about it carefully, is slightly misleading. But I propose to you some way to construct non-unique solutions by going a corner like this. So you start from the zero initial condition, and then this is a drawing at time t of your solution, and the height is t here, and minus t, t. You have this corner that starts to grow. And you see, on this counterexample, at least you have a point which is strong, which has a convexity really strong in one direction, and here in the other direction. And in some sense, it tells you that if you want to construct a counterexample, you have to have your second derivative be bending at the same time towards minus infinity and towards plus infinity. Something like this.
So you're saying this solves the equations without the convexity?
Yeah, exactly. So this would be counterexamples that do not have the convexity assumption inside, but start from an initial.
It does solve the equation, or it can be made to solve the equation.
Yeah, exactly. Yeah. I can cook up the slope. You see, I'm just gonna. So here I choose a slope of 1, but you can cook up the slope so that when you insert the gradient, you just match it. Okay, it's not hard to find affine solutions to this problem.
This is a vague question, but how does the phase transition survive in the limit with this viscosity?
Yes. So once you have identified this, the phase transition, we can read them on the derivatives. Like for what you want to draw, maybe in the end of the day, is a plot of this of the limit of this quantity, and this is a derivative of the object you compute. And it's also not too hard to show that at any point where the limit is differentiable, the derivative of the limit will converge to the derivative of the function will converge to the derivative of the limit. And so those points where f is actually not smooth are witnessing the phase transitions.
So maybe because in the Curvice, right, if h is 0, wait, let me think here. If h is 0, then it's just the free energy stays at 0, and then it starts increasing, all of a sudden, right? That's phase transition, right? But away from 0, though, it's not constantly 0. But if you were to draw the solution to this,
I can draw that
for each time.
Can I do
Yeah. Small times, then large times.
For small time, for small time, the solution will look a bit like a parabola, except the asymptote is -1 and 1.
Yeah.
This is the function itself, not the derivative. So if you think in terms of the magnetization, it's smoothly. I'm doing a drawing which is very small here, but it's transitioning smoothly from -1 to 1. This is for t small.
Are you plotting Fn or the limit?
I'm plotting the limit here, but
On the left picture is still Fn or is
this is the derivative of this. This is the derivative of this, which is the magnetization. At every point where this is differentiable, the limit of this is this. and here is differentiable everywhere, so it's fine. And now for t large, near the origin, it will look like the absolute value function. Okay, and then it's convex and it still has asymptote equal to 1, and so it's not so easy. I want to emphasize that it has a corners here.
So what happens at the phase transition, like when that develops, when the continuity develops? How does it develop? How does it?
Well, it's going to. I mean, you can study it precisely. You can compute the exponent. So here it looks like the absolute value. Here it looks like a parabola, and at the critical point, it will look like a power which is between. It's going to look like x to some power which is between 1 and 2, and one can compute it and okay.
So it goes instantly from quadratic to power to
some power, and then to absolute value. And then the graph is like this for the magnetization. Yes, and in fact, it's not difficult to really be precise about how this looks like, because another aspect I didn't say is that when you solve these equations, oftentimes, but not all the time, you can write the solution to this thing in a variational way. So I use PDE methods to identify the limit, but maybe it's like a proof technique. But once we have achieved the proof, we can double check, and in many cases we can rewrite the solution in a variational form. What are the many cases? Well, in particular, anytime the initial condition is convex, there is a variational formula for the solution. Okay, so in this case, it's a saddle point variational formula, and it's not always very easy to use. And at least it seems to me that using the PDE formulation is easier as far as the proof. When you have to write the proof, because you can use this principle, which is fairly robust. But once you have done the proof, if your initial condition is convex, you can just write a saddle point formula for the limit. It's also, when you come to spin glass models, actually the convexity assumption on the initial condition will not be valid. And so I want to also point out that in the case when the nonlinearity is convex, you can also write a variational formula. And this is how it will connect with the Parisi formula, actually. But in the case when the model does not have a convexity here, okay, I'm not sure what to, except speak about it. Okay, so in this paper with Hongbin and Jianmin, we used it to maybe I need to call this theorem to try to derive a rigorous version of the meta theorem that Lenka discussed this morning. So yeah, there were many contributors to this question, but let me. So it's about statistical inference, as discussed earlier this morning by Lenka. And we try to get close to what a meta theorem could look like. So we try to find some sort of general assumption for the problem we care about. So again, with Hongbin and Jianmin. So let's say the following: so fixed integers and some matrix. So there is a signal that we want to understand. I'm going to call it capital X. As Lenka explained, so n is the number of true variables in some sense, like it's your number of data points, if you want, and each of the data points, here we encode it as a k-dimensional vector, just like she was explaining that if you want to encode belonging to one group among k, you can encode this by using a vector of dimension k. Okay, so this data matrix, we're going to assume that it has independent and identically distributed rows. Well, we don't really need that, but okay, at least that's one assumption that makes things work. And we observe so what we some parameter some normalization times the p-fold tensor product of this matrix applied to this observation matrix A that is fixed and is of size which is not divergent. Okay, it's just some matrix plus noise. So just to clarify, so the tensor, I think it's like in Andreas talk in the morning. The way we think about this is as a okay, I'm not sure if this was. Well, anyway, so we think about this as a matrix of size n to the p times k to the p, and then it's multiplied by this matrix of size k to the p times l, and so in the end you get an observation which is like n to the p times l. Okay, and the L guy also is fixed, and you can think of it as doing being allowed to observe x in multiple scenarios. Like maybe you have 3 different sources of information about your data, and okay, it's a fairly general model because you can. If you give me the model of your preference, I can play a bit with what's exactly the way the data is given to me, or the A. So it's very flexible. And W is a matrix full of Gaussians independent. So then I'm not going to state the result exactly, but the claim is that under this model of statistical inference,
the A is known?
Yes, the A is known. Yeah. Also the law of the data is known. And the claim is that under these conditions, you can compute the mutual information between the data X and the observation. Then so there were many people who contributed to versions of this problem, and Lenka mentioned these people earlier this morning, but let me try to also do that. So people, for some choices of P and A, people derived versions of this result. So Florent Chakala, Lenka Deborova, Jean Barbier, Nicolas Macris, actually Angela Montanari, I think, also contributed. I think Emmanuel Abbé also did some work on this. Yash Deshpande, Léo Yolande, Marc Lelarge, Galen Reeves also, I think, wrote a very nice paper on this. And okay, now and also this one. So yeah, we are. So I think there is still, yes.
You're saying that the limit has a PDE formulation?
Yes, so I have to, the way I set it up here, if you write the mutual information, it will only depend on T. And so as stated, it's a little bit like if you're facing the Curie-Weiss model, and I have not introduced the H parameter, and you're like, how do I find a PDE if I only give you this? And so the first step is to devise an enriched version of your statistical inference problem. Or you also observe a linear, your observation is a linear function of the data plus noise. And that gives you then a problem which has a T as a function and also some matrix of size k to the p times k to the p. I said it's linear, but you can choose your linear function. And so you have a function of T and this matrix. And this function of T and this matrix is going to solve a PDE in the limit, which I can write down, but maybe a bit short of time. And it's convex in its variables, and so you can apply this thing. And moreover, at the end of the day, you can also write it down as a saddle point variational problem. I think there are cases that we cover with this theorem that I think would be difficult to prove as it stands with other methods. I think we're doing something which is a bit more than re-proving previous results. I could give an example which I think is only covered by our technique, but maybe I don't have a lot of time, so I stop.
Another question: can you make P depend on N?
A little bit, but not very much. So the proof can. We haven't tried to make the proof quantitative, but I think it can be done, but the rate will not be optimal. So I mean, at least I don't expect it to be so. So then, you get some rate, and so you can play a little bit, but okay, it's hard. All right, so I'm really super short on time compared with what I have planned to do, of course. So let me think about what I want to say next. So I forgot if you really made the distinction between the dense problems and the sparse problems. You talked about it, but this is really a setting with dense interactions between the variables. But you could also, okay, let's just say, you could also consider questions like community detection on a random graph, and you could make it so that the graph remains sparse even in the large n limit when the degree remains bounded. And this is not a situation that will be covered by this statement. Even sometimes you can say that asymptotically it will look the same or blah, 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 but if the degrees do not diverge in your commutation problem, then this will not be captured by such a result. And this is what we try to work on with Thomas Dominguez.
But just to get the picture, so how do exactly the enlargement look like in order to solve this problem, to prove the theorem? You have to do this enlargement of the model, no? So
Yes. So in fact, my plan was to discuss this for the spin glass model in the last 5 minutes I have. So maybe I'll introduce the SK model and say what it looks like, this enrichment.
Okay.
And so just to say, so with Thomas Dominguez, we tried to work out a version of this for this sparse community detection. But then the partial differential equation that is involved is of infinite dimension, and it's more difficult to explain, and we only have one bound for the moment. So we have not yet fully captured the mutual information in this case, although I hope that in the long run we'll be able to do so, and irrespectively of the number of communities or the details of the problem. So I have to admit that initially my main motivation was about spin glasses, and it's just that spin glasses are hard, and I thought maybe it would be good to understand this first. So in the last 5 minutes, I'm going to discuss spin glasses. I want to try to display how this PD point of view looks like for the Sherrington-Kirkpatrick model. So let me try to compute the free energy again. Or maybe I'm going to use a notation as in Andreas talk. Hn of sigma is the Hamiltonian of the SK model. Okay, I can enjoy that you define it already to define it. I like to normalize by this, but let's just, please forget about it. It just makes me happy, but it's fine. So far, this is just a function of t. And perhaps as a first guess, what you could do is add a random magnetic field to the problem. Because maybe you think that variations in the T parameter, maybe you will manage to compensate them by varying a random magnetic field. So let's try this. So Z dot sigma minus NH. So again, minus NH makes me happy, but just forget about it. Where Z is a vector of standard independent Gaussians. And I put a minus sign also. I'm not sure if it was a good idea, but that's what I did initially. So now this is a function of T and H. And we can compute derivatives again. If we compute derivatives in the T variable, what we get is that it's the average of the square of the overlap. And more generally, with the notation of Andrea, it's this function psi applied to the overlap. Where when we differentiate with respect to the H parameter, what we get is just the average of the overlap. Okay, so it looks very much like the Curie-Weiss model. That this minus this squared is the variance of something that is over the 1. And so plausibly, this variance will go to 0 as n goes to infinity, and everything will be fine. So unfortunately, as many of us know, in fact, the overlap does not concentrate when we are at low temperature, which means large T here. And so in fact, this equation that you write down here with just 2 parameters is only going to be with a 0 error term in the limit for small t. And for large T, what you need to do is refine the enrichment that is being plugged here. And yeah, we need to explain what you have to do, but maybe I'll just say in a few words. So the idea then is to try to have a magnetic field that mimics the way we know the Gibbs measure looks like. So we will sample a Poisson-Dirichlet cascade. So it's so there is a tree structure, and there are, okay, so I don't know how to explain this in 2 minutes. But let's say we want to do a K-RSB approximation. So we are going to have a tree somewhere that has a random probability measure on the leaves. So the leaves I'm going to denote n to, we can index them by the integers to the power of k. And on each of the nodes of this tree, there will be random variables. And with this construction, I'm going to define a random magnetic field that captures the sum of the structure of this. So
it is this random overlap structure in the terms of Eisenman-Simpson star with K-RSP, right?
I'm not sure, so let me write it down. So what I want to write is a random magnetic field that looks like this. So let's say sum this is h of alpha equals sum over k from 0 to k, let's say. So the parameters qk you give to yourself in advance, and you compute this difference. I like 2 just because I put square root of 2 everywhere. Okay. The difference between the q's, then multiplied by the Gaussian. So alpha is a guy on the leaves of the tree. Alpha vertical bar k is at depth k. Okay, and if you do this construct, then for alpha and beta on the leaves, you have that the expectation of, so it's a Gaussian field such that this property occurs. Okay, what you are things you give yourself in advance. And this is the construct. So if I choose, so here it's going to have to tell you exactly how I build my probability cascade. And here I just, I want to, this is a Poisson point process with some exponent. And here, because I think of a measure that has k plus 1 atoms of equal mass, I'm just going to take the exponent to be 1 over k plus 1 on each of these things, and then I do these k steps. Okay, and
the directions in space are just uniform random, or
the corrections in
directions in space, where these are pointing. I mean, this tree is embedded in space, right?
no, it's just a tree you do separately, and it's only indexed by. So now your system has two. Let's say it's a product space. There's the sigma variables that live where you decided them. Like there are +1, -1 to the n, and separately there are the alpha variables which live on this tree, okay, or on this side if you want. And your Gibbs measure has these two random variables, sigma and alpha, and they live.
It is a random external field. I mean, I
This is not z, right? I mean, the h of alpha replaces the z times sigma.
Yeah, this sub alpha slash k and the z's are all.
But in the formula for Fn, for the yes.
Yeah. So now it's h of alpha. Dot, and then okay, this is minus n cube k, and then you sum over the alpha, and it looks like this.
So this is
h of alpha.
The alpha is the weights of the cascade down there.
There is no
that's
square
the
root.
Eisenman-Simpson
The square root of
It is.
So there is also not square root of 2h, I guess. Just a cube.
Yeah, there is no square root, I think.
No, you need to differentiate.
Yeah, I raised this then. Sorry.
In the cube. The q is your other parameter.
And then the parameter is the measure is like this. Delta qk. Okay, and now you have a function of t and a measure, and the claim is that this function will solve a PD in the limit, which looks like this. And I'm going to stop here. Okay, so I don't have time to explain what that means, but this is the structure of the PD. And what's interesting is that when you try to look at models with multiple types, such as when you do things on 2 layers, what you want to write here instead of the square function is the product of something that depends on 1 layer and something that depends on another layer, but the product is not a convex function. And so the PD language gives you a way to speak about this, which otherwise I don't know how to get a handle on easily, because when it's convex, you have also this variational formula, but when it's not, I don't know. So sorry, I was very rushing a lot near the end, but okay, thanks for your attention.
Just the simple case. So in high temperature, you're having this concentration of the overlaps. Can you then, without using these cascades, can you, for instance, then analyze that, say, at least in some region?
Yeah, I suppose I haven't actually written this down rigorously, but for small t, you can justify that this PD is valid. And what I prove is
can you characterize the region where you can get it? So, or
I haven't tried yet.
Do you see that? Do you see the AT line in this differential equation?
I think you will have to come with a separate argument that says the overlap is concentrated, and then if you know that it's concentrated below the AT line, it's fine, but it doesn't spit out for you immediately the right region. But yeah, so one thing we proved is for these general models that include this 2-layer thing, we proved that the PD thing is an upper bound on the true limit for this object. So I have only one bound, but not the joint bound for the.
I mean, in the Curie-Weiss case, you had the 1 over n diffusion constant that was appearing. Here, I mean, I would expect the same thing, right? I mean, I would expect the correction.
Absolute value thing, and in fact, you see that's the problem. And when the function is convex, so I took a lot of time speaking about the Curie-Weiss case, but I think it's helpful because it really helps me to speak about this technical problem. And it's exactly that, is that the thing comes with the absolute value, and here I gave you a criterion to get around this. Assuming that the function is convex, the convexity assumption is not valid for the spin glass state. in statistical inference it works, and so any statistical inference problem that you give me, we're going to make it work. But in spin glass case, it's not, and then we're struggling to adapt this sort of selection principle in the other case.
So one question, in general, you get something like a variance on the
Yes.
side.
Yes, yes.
And okay, in the Curie-Weiss model, but how do you deal with just this variance term? How do you bound it?
So for, you mean for Curie-Weiss or for this model?
For this model.
So
whatever
for
model.
spin glass, let's say for spin glass. For the spin glass, in fact, once you have done this more sophisticated construction, now your GIST measure involves the variables the sigma and alpha, and when you compute the error term, it looks like this. So in fact, I'm going to add an identity. It's not an error term in this. For this function that I defined here, when you... Okay, so this is fancy notation, but the function I defined is the function of the qk's, and this just means you take the gradient of the qk's, and then you absolute value, you take the norm squared. This is what it is, okay. But for some reason I like to write like this. And now I'm writing the error term. So when you do the replica symmetric guess, the first thing I had written, what you find is that you find the variance of the overlap. But here you find this sort of conditional variance given the observation of the overlap between two copies on these leaves of the tree. And then the mechanism for explaining that this is small is the results of Panchenko on ultrametricity and synchronization. Even on the scalar case, I actually want to use synchronization here, because I want to say that if you tell me what is the overlap in the alphas, I can know what is the overlap in the sigmas. And so in this way, you can justify that in some, okay, it's an infinite dimensional PD, so it's hard to make precise sense of what I'm going to say, but essentially you can say that any limit will have to satisfy the solution almost everywhere. But as I said, this is not enough to identify what it does. And I can explain our attempts to bridge the gap, but...
For replica symmetric models, also you need a separate algorithm, the
yes.
argument that shows that they are replica symmetric.
Yes.
So you can prove that this right-hand side is small?
Yes,
But that is
by up to a small perturbation in the energy, I can, in the sense that I can borrow the arguments from Panchenko on ultrametricity and synchronization.
But that does not allow you yet to have a full proof of the Briggs formula.
Exactly, yeah, because you only say any limit will satisfy the equation almost everywhere, and that's...
Those algorithms, if you use those arguments, aren't you putting already the solution of the problem inside?
What do you mean?
I mean, if you use ultrametricity and synchronization, aren't you already saying what is the solution to the problem?
I mean, I'm proving. I mean, we know that up to a small perturbation in the energy function, the GIF measure will be ultrametric.
Right.
That is something we can prove, and in some sense, it's also built into the way this extra field is constructed. But the way you can justify that, I mean, you can justify that you can close the equation because we have these arguments of Panchenko that tell you that it's true. And I don't know, it sounds to me like you're saying I'm putting the solution inside the problem, but actually I don't know how to solve the problem right now. So even if I put all the assumptions inside, as you seem to say, I don't manage to prove the conclusion yet. So there's something not clear. Yes.
So yeah, I have a question which is probably related to what Silvio was asking. So do you have results finite k?
Finite k?
So say for one
so that's how we do it.
Paris split.
In the way we do the proof is we argue finite k and we control the error.
Yeah, okay, I understand, but say x to finite k, and for instance, because you see, the problem is that I want to say is the following: take k equal to 1, so 1 RSB. Take k equal to 1, so 1 RSB. And so, can you say something on the equation that you get? Even assuming that the error term is 0, pretending that this variance is small or is 0. Or something.
Then it's I think. Then it's an equation. I can solve it, and
You have existence uniqueness for that equation.
Yeah, but then how can you say that, for instance, the minimizer is...
So maybe I finally understand the questions you're trying to get into. So separately from this, we have a good solution theory for this equation. And actually, I wrote some okay, it was working, but was not very nicely put in the original paper. But Hongbin Chen and Jiaming Xia, without me, like really clarified perfectly nicely what is the solution theory for this equation. So we have a well-posedness theory for this thing. We know existence and uniqueness of solutions for this thing. You just have to say that that thing converges to that thing, but that thing itself is well identified.
I think we should stop here probably. And so the stuff is going to be here.